Hey guys, Ms. Gosling here. In this video, we are going to go over velocity versus time graphs, part 2. This time we'll be looking at accelerated motion. So by the end of this video, you will be able to analyze accelerating velocity versus time graphs. Now, one thing I do want to warn you about, this video is going to be a bit of a long one. If at any point you feel like you get the idea, you're welcome to skip forward, watch this at double time, and just make sure that you really understand the material before you move on. However, if you find that you don't need this full video to understand the material because it is mostly going to be different examples, again, feel free to stop when you feel you understand this content. So with no further ado, let's get started. So in this picture, I have an example of a velocity versus time graph. Now, as I hope you remember from the original video that we went over on velocity versus time graphs, the slope of the velocity versus time graph tells me the acceleration of my object, and the area between the line and the x-axis, which I've just highlighted, tells me the position of the object at given points in time. So with this graph, I'm going to go ahead and get started by figuring out the acceleration of my object. So what I'm going to do is I'm going to pick any 2 points on the graph, and I'm going to go ahead and pick this point and this one. And the reason I'm picking that, you'll see when I get into the math. So the original point that I've chosen is 0, 5, and the second point I chose is 5, 0. So to calculate my slope, so acceleration equals slope equals y2 minus y1 over x2 minus x1. In this case, y2 is 0 and y1 is 5. X2 is 5 and y2 is 0. So this becomes negative 5 over 5, or negative 1 meter per second squared. And that is how I'm going to calculate the acceleration of an object based off of its velocity versus time graph. I'm going to find the slope of that graph. When I turn that acceleration into an acceleration versus time graph, I know that at every point in time, my acceleration is negative 1 meter per second squared. So for every point in time, I will draw a little dot at negative 1, connect the dots, and I get a nice straight line at negative 1. Now, of course, if my velocity time graph had varying slopes, then my acceleration versus time graph would also vary, and we will see an example that looks like that. Next, I want to go through taking my velocity time graph and turning it into a position versus time graph. And to do this, rather than just doing 2 shapes, triangle number 1 and triangle number 2, I'm actually going to pick a few additional points. And the reason for that is because my position is not necessarily going to be changing at the same rate like it was in the graph that we looked at previously. That is, because my velocity is changing, because I am accelerating, I expect to see a curve in my position time graph. And in order to be able to really accurately picture that curve, I need to look at a few more data points than I would if I had a nice kind of straight line velocity time graph like we looked at last unit. So what I'm going to start with is I'm going to start at point number 2, or at 2 seconds, and I'm going to figure out the area under my graph at 2 seconds. So to do that, I'm going to break this kind of little quadrilateral shape into a rectangle and a triangle. This rectangle has a base of 2 and a height of 3. The triangle has a base of 2 and a height of 2. So the area at 2 seconds is going to equal 2 times 3, the area of my triangle, or the area of my rectangle, plus 1/2 times 2, which is the area of my triangle. That becomes 6 plus 2, or 8 meters. And that will be my position at 2 seconds. Next, I'm going to go ahead and look at 4 seconds. So between 2 seconds and 4 seconds, I again have this funky little rhombus shape. And I'm going to again break it into a rectangle and a triangle. In this case, my rectangle has a base of 2 and a height of 1, and my triangle has a base of 2 and another height of 2. So the area of my green shape is going to be 2 times 1 plus 1/2 times 2 times 2, or 2 plus 2, or 4. I'm going to add that to my previous position, and that's going to give me a new position of 12. Finally, for 5, I'm going to look at this little tiny triangle here, which is a base of 1 and a height of 1. And that's going to have an area of 1/2 times 1 times 1, or 0.5. So we're going to add that to my previous point, giving me a new area of 12.5. Now, I'm not going to go through the calculations for the rest of my graph. However, if you would like to go over them in class, I'm happy to go over them with you. But for 6, I'll have this little guy, which is going to have an area of negative 0.5, bringing me back to 12. For 8, I've got this area here, which is going to be an area of minus 4 since we are under the graph, and that's going to bring me down to 8. And then my final shape between 8 seconds and 10 seconds, I'm going to have an area of minus 8, which is going to bring me back to 0. So these are my positions for my velocity versus time graph. And what I'm going to do is I'm going to go ahead and plot those positions on the next slide. So on this slide, I have a few different things. So first, I have my points from the previous slide, which I've plotted on this graph here. And then at the bottom of my screen, I have a little sketch of what my original velocity versus time graph looked like to kind of help you visualize what's happening. So I think looking at this graph, how these dots should be connected probably feels pretty obvious, right? It looks very clearly like a parabola. However, what I want to talk about is why this shape looks the way it does. So as you can see, between 0 seconds and 5 seconds, my velocity is positive but decreasing. So my velocity is positive, but the magnitude of my velocity is decreasing. So what I expect to see is a positive slope, but I expect to see that my slope gets less steep between 0 seconds and 5 seconds, because that is how I represent the fact that my object is slowing down. Now, after 5 seconds, my velocity is negative, and I can see that because I go to the negative part of the graph. And my speed is increasing, so I'm getting faster. So I expect to see the exact opposite thing that I saw in the first half of my graph. I expect to see slopes being negative, and I expect to see my slope getting steeper, which you can see in my graph. If I was going to draw my tangent line at the beginning, at a random point on either side of the graph, and at the end, you'll see my slope starts positive and steep, then it gets positive and it starts positive and steep, then it gets positive and shallow, negative and shallow, and finally negative and steep, matching what I see in my velocity versus time graph. So we've done one straightforward question. Next, what I'd like to do is I would like to do a slightly more complicated question. So in this graph, I have a velocity versus time graph where my acceleration is no longer constant. So what that means is I'm going to have to split my graph up when calculating my acceleration into sections of constant slope. This is very similar to how we went from a position versus time graph to a velocity versus time graph in the previous unit. We're finding our sections of constant slope. We're going to find the slope of each of those sections. And then we're going to plot our acceleration versus time graph, and we're going to expect it to look kind of toothy, just like our velocity versus time graph did in the previous section. So I want to start by looking at sections 2 and 4, where I have a horizontal line. When my line is horizontal, that means that my acceleration is going to be 0 meters per second squared. So from 4 seconds to 5 seconds, and from 7 seconds to 9 seconds, my acceleration is 0 since I have a flat line. Next, I'm going to look at my first section. I'm going to go ahead and pick 2 points, and I'm just going to pick the 2 points at either end. So 0, 0, and 4, 4. And I'm going to calculate the slope of that section. So the acceleration from 0 to 4 is going to be 4 minus 0 over 4 minus 0, or 1 meter per second squared, which I'm going to go ahead and put on my chart. Finally, I'm going to look at my last section. I'm again going to pick my original point, which is 5, 4. And I'm going to go ahead and look at my final point, which is 7 and 2. And I'm going to go ahead and calculate my slope. So my slope from 5 to 7 seconds is going to be y2, which is 2, minus y1, which is 4, over x2, which is 7, minus x1, which is 5. That becomes negative 2 over 2, or negative 1 meter per second squared, which again is going to go into my chart. Now that I have successfully calculated my slope for each section of my graph, I can go ahead and transition that into an acceleration versus time graph. So I'm going to take all of my data and plot my points. So between 0 seconds and 4 seconds, my acceleration is 1. Hence why I have a line going from 0 seconds to 4 seconds with a y value of 1. Next, from 4 seconds to 5 seconds, my acceleration is 0. So I again have that horizontal line from 4 seconds to 5 seconds. And I'm going to go ahead and make this black. And then I want to connect my lines with a straight up and down vertical line because my acceleration is changing instantaneously. So next, I'm going to look from 5 seconds to 7 seconds. I have an acceleration of negative 1, and I'm again going to go ahead and vertically connect that to to the rest of my line, to my previous point at 5. And then finally, from 7 seconds to 9 seconds, I again have a velocity or an acceleration of 0, which I'll go ahead and connect with a straight up and down vertical line to my previous acceleration. So just so you are aware, you will know you have done your acceleration versus time graph correctly when your graph looks boxy. So we should see shapes like this. I should not see shapes like that. That is not what our acceleration time graph will look like. We're always going to have boxes. So we've done acceleration versus time. Let's go ahead and take a look at our position versus time. And for this position versus time graph, what I'm going to do is I'm going to go ahead, I'm going to break this into a few different shapes. So I'm going to look at 2 seconds, 4 seconds, 5 seconds, 7 seconds, and 9 seconds. And I'm going to write whether my acceleration is positive, negative, or 0 for that time frame, as well as calculating my position. So in this first section, I have a nice, easy triangular shape with a base of 2 and a height of 2. So we're going to have an area of 1/2 times 2 times 2, or 2. So I'm going to add that 2 to my previous position, giving me a new position of 2. And in that time period from 0 to 2, you can tell my acceleration is going to be positive, and my velocity is positive. So what I'll see is that my object is speeding up in the positive direction. So I expect to see some sort of shape like so in my position time graph. Looking at my next point at 4 seconds, I'm going to go ahead and look at this shape. So again, I'm going to break this down into shapes I recognize. This one has a base of 2 and a height of 2. And my triangle has a base of 2 and a height of 2 as well. So my area is going to be 2 times 2 plus 1/2 times 2 times 2, or 4 plus 2, or 6. So I'm going to add that 6 to my previous point, putting me at 8. And again here, my acceleration is positive, and my velocity is positive. So I again expect to see a curve that is increasing in its slope in the positive, it should have a positive slope that is getting steeper over time. Next, I'm going to look at 5 seconds. So at 5 seconds, I've got this nice yellow triangle with a base of 1 and a height of 4. So my area is going to be 1 times 4, or 4. So I'm going to add that to my previous spot. I have 8 plus 4, so my new position is going to be 12. In this case, my slope is 0. So I expect to see a straight line. In this case, since my velocity is positive, I expect to see a straight line with a positive slope. So a nice straight uphill line. I'm going to go ahead and draw a little slash through my 0 so you can tell it's a 0 and not a circle. Next, I'm going to look at 7 seconds. And this one is a little bit tricky looking. So as you can see, I have to get, so for this shape, I need to get the space between my line and the bottom of my graph, which is in fact all of this space, even though you can't see anything over here. So I'm going to go ahead and I'm going to figure out both this triangle and the rectangle. So in this case, my triangle is a base of 2 and a height of 2. Or sorry, my rectangle is a base of 2 and a height of 2. And my triangle has a base of 2 and a height of 2 as well. We've seen this before. This is an area of 6. So I'm going to add 6 to my previous position, putting me at 18. Now, one really common error that I see is people will say, oh, this line is downhill. Therefore, my velocity is negative and my position is decreasing. And I want to make sure you guys know that is not correct. My slope being downhill means that my acceleration is negative. But since my y values, i.e. the numbers on my y-axis that are associated with this part of my line, they're all positive. So what that means is that my velocity is still positive, I'm just slowing down. So my acceleration here is negative, but my velocity is positive still since my numbers, my y values are all positive. So I expect to see something like a logarithmic graph where my slope is getting shallower, we're getting less steep over time. But again, my slope is still positive because my velocities are still on the positive side of the y-axis. So next, I'm going to look for the rest of my graph between 7 seconds and 9 seconds. So this is going to be a rectangle with a base of 2 and a height of 2. So we are adding 4 to our previous spot, since that is going to be the area under the curve there, making my final position 22 meters. In this section, my acceleration is again going to be 0, but my velocity is positive. So I expect to see another straight line with a positive slope when I graph this point. So let's go ahead and get graphing. So over to the right here, I have a summary of my little data table from the previous screen. And to the left, I have my position time graph with the plots all pointed for you, with the points all plotted for you, so we don't have to go and plot all the points. So first, I'm going to look at my first section, where where I'm going from 0 seconds to 2 seconds, and I'm going from 0 meters to 2 meters, and I have a positive acceleration. So again, I expect to see my slope increase. So I'm going to draw that with a nice increasing slope, like so. I'm going to go ahead and erase this and get it a little bit nicer looking. There we go. Similarly, from 4 seconds to 8 seconds, I am going to continue to see my slope of my graph increase. So I should have this nice kind of smooth curve from 0 seconds to 4 seconds. Then from 4 seconds to 5 seconds, I now have a slope of 0. So I expect a straight line. So I should see that curve disappear. Next, from 5 seconds to 7 seconds, my slope is going to start to decrease. So I'm going to see a little bit of that kind of uncurve there. We're going to kind of do that little frowny face curve. And then finally, and you can see it's a little bit subtle. I may want to make it a little more noticeable. If I was going to do if I was you and I was doing this on a test, I might make it a little more noticeable to show that I understood that my slope was decreasing. And then finally, from 7 seconds to 9 seconds, again, I'm going to have a nice slope of 0, like so. And this is my position versus time graph for an object with varying acceleration. It's a little bit ugly looking, but that doesn't mean that it is not correct. So with that, let's go to takeaways. So first of all, the area under an acceleration versus time graph gives you position, and slope gives you acceleration. And I'm going to go ahead and cross this off and write the word acceleration because I've clearly made a bit of a typo here. On a velocity versus time graph, a diagonal line indicates acceleration. And on a position versus time graph, a curved line indicates acceleration. So if I have a velocity versus time graph, any diagonal line, like so, indicates that my object has an acceleration that is not 0. On a position versus time graph, though, a straight line does not indicate acceleration. Rather, to see acceleration, I need to have some kind of curve to show that my acceleration is not 0. And there you have it, folks. This is how we can graph slightly more complicated velocity versus time graphs. So with no further ado, it is your turn to get some practice graphing. Best of luck and happy solving.